start with a controllability in state space. So, what is meant by a controllability? So, it is said that if the system states transfer from any initial state x of t naught to any other desired step x of t f in a specified time by an unconstrained control vector u of t. That means, these are system states, they are called initial state. Now, because of this control input, they will transfer to a finite state x of t f. That means, this we are talking about x dot equals to a x plus b u. The states at some initial time and it has been transferred to the final state and the system is controllable. Then how do you think about this in a general way? For example, an industrial trip is going from say one place to another. Let us say now we are here in say in IIT Roorkee, and now here I have to take out some students from IIT Roorkee to say some industry at Delhi. So, the IIT Roorkee is there campus, then there is the industry is there, and I have to take let us say 10 students. Now, we will define the 10 students as 10 states x 1, x 2 to x 10. So, the 10 states or 10 students are present in IIT Roorkee before travelling, and now we have started travelling from IIT Roorkee to some industry at say at Delhi, which is in India. So, what happened at t equals to say at 5, it has been started and it has to reach at some time. So, what happened, all these states are available at initial time, sometimes you can say that it can be at a t 0. So, these states are available at some initial time, but when these states or the student has been transferred to say Delhi, say it should be x 1, x 2 up to x 10, but when this student trip has been transferred to Delhi, out of this let us say this is x 9. So, let us say this x 9 state or x 9 student is not present. So, as that means, when this bus for which I am taking my students, when they reach to Delhi and I have to take these students to some industry, and when I started counting the students, instead of 10 students I have observed 9 students. So, if the 9 students are observed, one is absent in that particular group, in that particular stage, then what will happen? Can I take the student to industry? Because this is a responsibility for me to take care of all these students. When I observe that the student is not there, it means that it is a very tough work for me. I have to identify where is that student, and I will do this process, and if I have not found that day, it is better for me to take this student back. That means our work cannot be completed. It means that your system is not controllable. That means what we want, as we apply input to the system, whatever the states are there, that after applying input the state must be transferred. That state must not be ideal, and the state is, if the state is ideal or it is not although it present, but it is not doing its work, that means that system is not controllable, and when the system is not controllable, we cannot design any controller in that case. Therefore, this concept of controllability is very much important in a state space application. That means we cannot design any controller if we can't test the controllability of the system. The question has come, how to check the controllability of the system. Now, testing of the controllability. So, if you see the literature, there are two tests, one is called Kalman test and other is called Gilbert test. Both have been used to check the controllability of the system. Now, first of all, we see the first test, Kalman test. The system represented by x dot equals to ax plus bu. here I have not written equation of y because the state here is concerned with x and u, there is no relationship with the output. Therefore, when I am talking about the Kalman test, I have written x dot equals to ax plus bu. So, this system is completely state controllable if and only if the rank of this combined matrix, that is B, AB, A raised to n minus 1 B is n. The rank is n, that means that determinant of QC should be non-zero. If this QC is 0, it means that system is not controllable. That means the determinant should be non-zero, it means that rank of this system is n, and in that case we can say that system is controllable. Then again here a point has come, why it is like this, why we are saying that for controllability we require B, A, B, A raised to n minus 1 B. Now we will see the proof for this. Now for this particular case we have seen the state response. The state response we can write down as x of t equal to e raised to a t x naught. So 0, initial time 0, so Tf e raised to a Tf minus tau b u tau d tau. Now here is the state equation, x dot t equals to e raised to a t x naught 0 to Tf e raised to a tau f tau b u tau d tau. Now what is the final state? Now we are considering the final state is say your origin. So final state is a origin, that means what I am saying x of Tf, this final state origin, that is equal to e raised to a Tf x naught 0 to Tf e raised to a tau f minus tau b u tau d tau. Now here final state is origin. So origin means we can write is as origin 0. So 0 equals to e raised to a Tf x naught 0 to Tf e raised to a tau f minus tau b u tau d tau. Now this origin is there. Now we can write down the equation of x naught as x naught equal to minus 0 to Tf. Now this is plus e raised to a Tf. So when we take one side we can write down as e minus a Tf. Now this e raised to a Tf multiplied by e raised to minus a tau b u tau d tau. So now this cancelled. So we can write this x naught equals to 0 to Tf e raised to a tau b u tau d tau. Now about this part e raised to a tau, this a raised to a tau b u tau d tau. So how to write down this e raised to a tau? So we know the Cayley-Hamilton theorem. Now here we will use the concept of Cayley-Hamilton theorem, that is every square matrix satisfies its own characteristic equation. We have already seen this in a state transition matrix. Now this part we can write down in terms of Cayley-Hamilton theorem, e raised to minus a tau, that is equal to plus alpha 1 plus alpha 2 and this process limited. So this equation can be written as k 0 to n minus 1 into a raised to k. Therefore the equation can be written as x naught equal to minus 0 to Tf k equal to 0 to n minus 1 into A k B u tau into d tau, and this equation finally can be written as k equal to 0 to n minus 1 a raised to k b 0 to t f alpha k tau u tau into d tau. So, now this equation we have obtained, and now afterward this equation can be written as 0 to t f, particularly this part alpha k tau u tau d tau, let us say equal to beta k, and therefore finally this equation can be written as x naught equal to minus k equals to 0 to n minus 1 a k into beta k, and this equation finally we can simplify it as x of x naught equal to minus b a b, say a raised to n minus 1 b, and this is multiplied by this beta k as beta naught beta 1 up to say beta n minus 1. Now, here x naught is there and this equation is there, this is to be satisfied. So, this is satisfied, that is initial condition x 0 equal to this is satisfied only when this particular part b a b a raised to n minus 1 b should be non-zero. So, when this is satisfied, then and then we can get the controllability of the system, or we can say that x 0 will be satisfied, and therefore, this b a b a raised to n minus 1 b is the controllability test of the system. That means, the whatever the Kalman test, this Kalman test, that is to check the controllability of the system, we have to check the rank of b a b a raised to n minus b. Now, we will see the example. Suppose the system is represented by x dot equal to 0 1 minus 1 minus 2 x plus 0 1 into u, and our question is we have to check the controllability of the system. Now, this is A matrix and this is a B matrix, and now here we have to use our Kalman test, that is x dot equals to a x plus b u, b a b a raised to n minus 1 b. So, here we can write the controllability matrix q c as b a b. That means, here we need the multiplication of A and B matrix. So, this A B we can write down as 0 1 minus 1 minus 2, and here B as 0 1, and if you solve it, so here get 1 and here minus 2. So, B is our 0 1 and here is 1 minus 2, this is QC matrix, and now what we want a determinant of this matrix. So, determinant of this matrix is QC 0 1 1 minus 2, and if you solve it we will get here as minus 1, this is non-zero, and therefore, we can say that this system is controllable. So, here simply determining the B matrix, simply writing B and AB, or in terms of A raised to n minus b, when we can get the controllability of the system. So, here we will find that this controllability test from numerical point of view is quite easier, but we will find that we are not getting the insight of this controllability. Why this means, why this type of thing is happened here, or let us say if it is not controllable, why it is not controllable, that information we cannot get, because whenever we are dealing with the system, we must know that out of these different state which particular state is not controllable, so that some remedy we can make if required that time, but this type of informations cannot be achievable by means of this Gilbert this Kalman test. So, in that case there is another test that is called Gilbert test of controllability, and based on this Gilbert test we can get some information about the inside of the system, that means which is the particular state which is not controllable. That information can be achieved by means of this Gilbert test. So, we will see what is this Gilbert test of controllability. So, the Gilbert test of controllability is based on the concept of diagonalization. In that time I had explained you the concept of diagonalization. That time I had told you that this diagonalization is helpful in checking the controllability of the system, and as I discussed earlier that before checking going for the controller we have to check the controllability. That means whatever we have studied earlier, that has been very much important in a controllability as well as the control design. Now, we will again see the concept which we have seen last time, that is about the diagonalization and how this diagonalization is useful in checking the controllability. We will see it. So, we start with our original model as x dot equals to ax plus bu. As I told earlier that we have not taken a y, because y is not required here, it is concerned with x and u only. Now, in case of diagonalization we are defining a new state, that can be any state, any variable. Just now x, we can define a k variable. So, now here using state transformation, say x equal to m into k and this k equal to m inverse x, and now here we can write down k dot equal to m inverse x dot, that is equals to ax plus bu. So, afterward we can write down as k dot equal to m inverse ax plus m inverse bu, and now here m inverse a, what is x? X equals to mk plus m inverse b into u, that is k dot equal to m inverse a m into k plus m inverse b into u, and this is nothing but k dot equal to a bar k plus b bar into u. So, now this equation we have got. Normally when we are written equation just like x dot equal to ax plus bu, and when we have converted the original equation in this form, this a bar it is in a diagonal form, and therefore, this equation we can write down as k1 dot k2 dot up to kn dot, that is equal to lambda 1 lambda 2 up to say lambda n, here k1 k2 kn, and here b1 bar b2 bar bn bar into u. So, now this equation, that is ki dot equal to lambda I into ki bi bar into u, that is I equal to 1 2 up to say n, and if you solve this equation we can write down as k of Tf e raised to lambda I into t ki 0 plus 0 to Tf e raised to lambda I Tf minus tau bi bar u tau into d tau. So, now here just like x dot equals to ax plus bu, we determine x of t, here we are defining ki of Tf, this is the final time equals to lambda I Tf x ki 0, this is our unforced part and this is the forced part. Now, we simplify this. So, this equation can be written as Ki Tf minus Ei lambda I Tf Ki 0 divided by E lambda I into Tf equal to 0 to Tf e raised to minus lambda I tau Bi bar u tau into d tau. So, now this equation has been got. Now, but here till date we have not understand that where is the controllability part has come. So, now if you see, if these particular elements, this is concerned with u and k1. So, k1 is one of the states. If any of the elements is 0 here, so similarly here if any of the elements is 0 here, there is no connection between the states and u. Therefore, this particular part, this is Bi bar, this is nothing but concerned with the Bi, B1, B2 bar, Bn bar. So, that should be non-zero. If any of the elements in this particular column is 0, then we can say that system is not controllable. That is particularly if you say this part, this Bi bar, if any of this be 0, there will be no connections between the input and as well as the states, and therefore, to check the controllability of the system, what we can do that none of the 0 in this particular column should be that means none of the elements in this column should be 0. Now, this is the case which we have taken when there are eigenvalues are distinct, but the case may be different when your eigenvalues are repeated. That means, let us say your k dot equal to j k plus b bar into u, and j bar is particularly in the Jordan form. This is called Jordan form. Jordan form, it means that you are having the repeated eigenvalues. So, when the repeated eigenvalues are there, how to check the controllability of the system? So, when the Jordan form is coming, it means that in the Jordan form, let us say here lambda 1, say 1 0 0 lambda 2 1 0 0 say lambda 3, then there can be another, this is one block, this is one block, and there another block, let us say lambda 4 1 0 lambda 5, and here let us say lambda 6 lambda 7 up to say lambda n, if and rest of the elements are zeros, all are zeros. Here these are diagonal elements lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, 6, and these are the Jordan blocks. And the main thing is that how to check the controllability in this case. So, in that case we have to see the end of the Jordan blocks. Let us say this is the end of the Jordan block. So, here whatever elements of B bar, that should be non-zero. That means for this case this one, and for this case that B bar should be non-zero. If any element here or the element concerned with the end of the Jordan block is 0, then we can say that system is not controllable. So, here from this we can get the insight of the system, that means which particular state is not controllable. That means here also we have seen that if any of the state, let us say this is B1 bar is equal to 0, it means that this K1 dot is not exist in our system. Therefore, that particular state we can isolate it, and finally, if you take this state into account, the controller design cannot be possible. Now, we will see one example, say x dot equal to 0 1 minus 4 x plus 1 minus 2 into u. Now, here if you calculate the eigenvalues of the system, so we will find that the characteristic equation for this system is lambda I minus a equal to lambda square plus 4 lambda plus 4 equal to 0, and here lambda 1 equals to minus 2 and another lambda 2 equals to minus 2, and here as this is in a companion form. So, the model matrix AM you can get at 1 1 here we will get it as minus 2 and about this particular minus 2, but this particular part is wrong, because when the eigenvalues are repeated. So, in this case the first particular part, the eigenvector corresponding to this we can write down as 1, this is lambda equal to 1 minus 2, and corresponding to this m2 what we have to take? We have to take differentiation of 1 by lambda, that is at lambda equals to minus 2. So, here we will get 1 say 0 and here 1, and therefore, the model matrix in this case we will get it as 1 minus 2 0 1, and here m inverse am will get it as minus 2 1 0 minus 2, this and this b bar, this b bar that is equal to m inverse b. So, here your m inverse is 1 2 0 1. If you calculate the inverse of this, m will get 1 0 2 1 and b as 1 minus 2, and if you solve it we will get 1 0. Therefore, this k dot equal to a bar k plus b bar into u. So, we can write down this as minus 2 1 0 minus 2 k plus b bar as 1 0 into u. Now, you just see here, now here comes 0 and here is minus 2, and as discussed earlier, the particularly end of the Jordan block. So, this is Jordan block end, the corresponding element should be non-zero, but here it comes 0, that means that this system is not controllable. So, in this way we can check the controllability of the system. In this particular example, the most important point we observe that here about the writing the elements in the as a model matrix. Here we will find that we have started with the writing the am, and because this is a companion form or controllable canonical form, we have to write down a Van der Monte matrix as 1 1 lambda 1 lambda 2. But in this particular case the eigenvalues are repeated, that is why initially we are writing eigenvalue as 1 lambda, that is 1 minus 2, but another one is minus 2. So, same eigenvalue cannot be written. Therefore, what we have done, we have taken differentiation of this one and then we have got 0 1, and in this way m we have determined, and then we have determined m inverse am and b bar equals to m inverse b, and finally we come across this result, and but this particular element is 0. 0 is corresponding to this Jordan block, therefore, system is not controllable. So, here one example I have solved. You try to solve many examples as possible and check the controllability of the system. You can also check the controllability of the system for multi input multi output system and see the what way you are getting the result. Now, these are some references. Thank you.